Hello fellas. Today we will be talking about the traveling salesperson problem. This is a subset of graph theory that deals with optimization, typically optimization of distance or cost. The traveling salesperson problem is named for salespeople that must complete a circuit through several different cities and want to find the least distance. Now, as a graph, these cities and their corresponding distances are represented with the cities as the vertices and the distances as the edges. For our problem today, we will use a graph of 4 cities. So we will have 4 vertices as City 1, City 2, City 3, and City 4, and 7 edges, representing the different distances between the cities. Now this graph right here can be translated into this matrix, with the matrix row number representing the starting city, and the matrix column number representing the ending city. Therefore, the trip from City 1 to City 2 has a distance of 10, as shown in the graph. Now, this graph kind of throws you for a curve here, because we have 2 different values for City 1 and City 3. City 1 to City 3 has a distance of 7, whereas City 3 to City 1 only has a distance of number 6. This could be, in the real world, anything from road work being done on the highway from City 1 to City 3, or different airfares causing there to be a different distance number or time number. And so we should see this in the graph as from City 3 to City 1 we have a value of 6, but from City 1 to City 3 we have a value from 7. Now, what we do now is we're going to try to find the minimum bound. So we're going to subtract each row by the smallest number in the row in order to get a minimum bound. So for row 1, we're going to subtract by 7, which will give us a value of 3 from 1 to 2, 0 from 1 to 3, and 8 from 1 to 4. For 2, we'll subtract by a value of 6, giving us a value of 4 from 2 to 1, 6 from 2 to 3, and 0 from 2 to 4. Now you might be wondering why we have dashes, and the dashes represent an invalid trip. We're not going to go from City 1 to City 1, we're not going to go from City 2 to City 2. Therefore, we have dashes instead of an actual number. So, when we subtract all of the smallest numbers from each row, we're going to get 7 plus 6 plus 5 plus 5, which is going to give us the minimum bound of 23. Now this represents the least distance we're going to have to travel if we throughout this entire graph. Now what we do is, to continue establishing this minimum bound, we're going to subtract each column by the smallest number in the column. So for for column 1, we're going to subtract 1, which is going to give us 3, 0, and 9. And for column 2, we're going to subtract 1, which is going to give us 2, 6, and 0. So this is going to increase our minimum bound to 25. Yeah. So 25 is going to be the least distance we're going to have to travel in this entire graph. So now we're going to have to make a choice here. This is called a branch. We're going to choose a 0 number, and for this time we're going to choose 1, 3. And we're going to have to make a choice whether we're going to use 1, 3 as one of the trips on our circuit, or we're going to have to choose whether we're not going to go 1 to 3 as one of the trips. So the first choice is going to be we're not going to use 1 to 3. So we put a dash because it's going to be an invalid trip. So this gives us the new matrix, this matrix where 3 is a dash. So what we do now is we establish a new minimum bound where we subtract by 2 down in this new matrix. And so we have a new lower bound, new minimum bound of 28. And so our second choice is, if we do travel from City 1 to City 3, we're going to eliminate row 1 because we've already used City 1 as a starting point, and we're going to eliminate column 3 because we already used City 3 as a destination. And so this will give us a new matrix of this new matrix. And so what we're going to do now is we're going to find the minimum bound of this new matrix by subtracting 3 from column 1, which will give us this matrix. because we subtracted by 3, our new lower bound will now be 28, which is 25 plus 23. So because this lower bound is higher than, this lower bound should not be 28, it should be 27 for 25 plus 2. So since the lower bound, if we do travel from city 1 to city 3, will be 28, and the lower bound, if we don't travel from city 1 to city 3, will be 27, we do not want to travel from city 1 to city 3 because it has the smaller lower bound. The smaller lower bound. And so, now we're going to have to make another choice, whether we travel from city 1 to city 2. And so, our first choice, this is another branch. Our first choice is if we do not travel from city 1 to city 2. We put a dash at the column, the row of city 1 and the column of city 2. And since our only remaining value in this row is 6, we subtract by 6, and this increases our lower bound by 6. So our lower bound, if we do not take the path from city 1 to city 2, is 33. And since that's higher than our trip to city 3, we know we're not going to go from city 1 to city 2. And so if we do take city 1 to city 2, we eliminate row 1 because we've already used city 1 as a starting point, and we eliminate column 2 because we've already used city 2 as a destination. And so we get this new matrix. And we cannot subtract anything from any columns or any rows, so our lower bound continues to be 27. So we're going to branch again. We're going to have to make a choice whether we go from city 2 to city 4 or we do not go from city 2 to city 4. So if we do go from city 2 to city 4, we put a dash. If we do not go from city 2 to city 4, we put a dash at point 24 because that's an invalid trip. And we have to subtract row 2 by 6, and we find our new lower bound is 33. If we do go from city 2 to city 4, we take away row 2, as we've used 2 as a starting point, and column 4 as we use city 4 as a destination, and we get this new matrix. We also put a dash at 4 to 1 because if we go from city 1 to city 2 to city 4, then we have to go to city 3. We can't go to city 1. If we go to city 1 from here, then we have a sub-circuit of just 1 to 2 to 4 to 1. We leave out city 3, so that's no good. We have to put a dash there to prevent us from having there. And since we can't reduce that we can't take away anything from the columns or the rows, our lower bound remains 27. And because we have a matrix where there's only zeros, from here we know that we have to go from city 4 to city 3, and then city 3 to city 1 in order to complete the trip. So this gives us the shortest path of city 1 to city 2 to city 4 to city 3 to city 1. And then since our lower bound is 27, we know that the journey's value is going to have to be 27. And we can check this by going back to the original graph. We see that city 1 to city 2 is going to be a value of 10. City 2 to city 4 is going to be a value of 6. City 4 to city 3 is going to be a value of 5. And city 3 to city 1 is going to be a value of 6. Yes, and so this is going to give us the final value of 27. So it checks out. Now you can use this for problems with more than 4 cities, more than 5 cities, up to any amount of cities. This works perfectly. Thank you for watching. I hope this helped, and leave a thumbs up if you enjoyed this.